So mu is the path with the player who changes j minus 1 is 1 by the definition of zj. And another thing which is important is that we can now conclude that basically I mu with u is equal to I gamma with u. Because look at the following illustration. So gamma is defined as S0. Then we move to S1. Then we move to through some steps probably to Sj minus 1, then to Sj, then to Sj plus 1, and then again through some steps we move back to Sl, which is equal to S0. Now that path can be changed by replacing Sj with Zj. And look at the following circle: Sj minus I, Sj, Sj plus I, and Zj. It's I0. It's a simple closed path of length 4. And therefore, we can just say that we can conclude that going from Sj minus 1 through Sj to J plus 1 or through Zj gives the same addition to the I. And therefore, by replacing that piece with that piece, I remains the same. So I of mu with u is equal to I of gamma with u. Okay, so we have arrived at a path mu which fulfills the requirements of gamma, but here j, the place, the other place besides the zeroth place, where I is the place of change, is now j minus 1. And we can recursively go in the same way. Eventually we have to arrive at I0 equals to I1, which is a contradiction, as we said, because j has to be between 2 and L minus 2. So we have arrived at a contradiction, and that contradiction concludes the proof that 4 implies 2, and that, as I already said, concludes the proof of the theorem. So I remind you that the theorem is that this statement equivalent G is a potential game, or I of any finite closed path gamma and with u is 0, or for any finite simple closed path gamma, I gamma u is 0, or for every finite simple closed path gamma of length 4, I of gamma and u is 0. So being a potential is equivalent to each one of those statements, and that's of course very resembling of the physical characterization. Now we are going to also show a very simple conclusion from the fourth statement, so that for every finite simple closed path gamma of length 4, I0 is equivalent to having a potential. And the conclusion is as follows. So a game is potential if and only if for any two players I and J, for any sub-profile of the others S minus IJ, and for any two strategies for I and J, Si and Ti and Sj and Tj, the following sum is 0. And we simply the proof is, even to understand this, it's easier to look at the proof. That we simply consider, as the theorem said, as a general finite simple closed path of length 4, which, as we have proven, is equivalent to being a potential game. So we denote this as this path as A, B, C, D, A. Now that the players who change their strategies denote them by I and J, and that's how we get to this characterization. Of course, a four-length closed path can result not from a single but also from two deviating players. But if it's only one deviator, then the sum of the utilities of the deviator along the path will be 0 trivially. So the only condition which we need to write is what happens when we have two different deviators. Okay, so we are done with the physical characterization, and now let us move to the last point about potential. Games which is using potential as a refinement of the Nash equilibrium. So we have said that being a point in the strategy space which maximizes the potential means that that point also is a Nash equilibrium. Because if you maximize the potential, then it means that potential cannot increase if a single player changes her strategy, but by the definition of potential, of exact potential, the difference in the potential will be exactly the difference in that player's utility. So no player can increase her utility. But a maximum of potential is not necessarily every Nash equilibrium. It's only a subset in general. And that's something we have seen in the tutorial. And that is important. So knowing that subset gives us a way to have a special subset of Nash equilibria, which means that it's a refinement. Now it's important to notice that since all the potential functions, exact potential, I remind you, differ by a constant, then maximum of potential is invariant of which potential function you choose. So it's well defined, the set of points which maximize the potential. So it's a refinement concept. Of course, when there is a set of points which maximize the potential. And let us look at an example which also involves a very famous game. So first let's look at a very classical game by Stack, which called Stack Hunt, which Rousseau apparently, at least he was the first person to speak about that. It describes the importance of cooperation. So imagine that you can choose whether you want to hunt stag or hare. So stag is a deer, it's a big animal, and hare is a small animal, of course. And if you hunt a stag, you need someone's help. So if the other person hunts hare, you will have a very small chance to find the stag, and given the effort you are investing, your total utility is going to be 0. However, if you both decide to hunt stags, you will manage with high probability to find the stag, and since it's a big animal, your total utility is going to be high, 4 each. Now, if you decide to hunt hare, you don't care about the other person. You don't need their help. You will get your 3 without, regardless what they do. It's not so much, but it's less than 4, but it's okay. So here there are 2 Nash equilibria. 4 instead of 3. And of course, for 4 is better for everyone. But there you depend on the other person. And if the other person changes, it is not to their best interest. It's not in their best interest. But if they do change, because then you would suffer. But you will suffer. But in the case of the other equilibrium, you will not suffer, even if the other person changes. So we can say that while the stack is better, the HH hare is safer. Okay. Till now was the classical stack hunt game, and now let us look at the generalization by Crawford in 91, so many years after Rousseau. And that is simply a generalization for any number of players as 1 till as n other strategies. And let's here choose the amount of effort, not like 2 options, but any number. Here it's 7, but it can be anything. And the amount of effort of each player is from 1 to 7. And the utility of a player is as before. You first look at the minimum investment, which is what you can get as a team. Can you get a stag, or you can only get something small? And the minimum investment, you also need to subtract from it your effort. So it's A, some parameter times minimum investment, minus B times your investment, plus some parameter C, which just makes sure that the utility is positive. So now look at the game by Crawford. And that's a potential game. And the potential is the following. It's like the utility. It's A times the minimum investment minus B times the total investment. Now, why? Because if a player changes what she does, her utility changes as the minimum investment minus B times her investment. And that's exactly the change to the potential. So minimum investment minus B the total investment if one of the players changes. And the potential, her maximum is defined as follows. So it's as follows. If A is smaller than n times B, so if A is too small in order relatively to the effort, in order for you to act well, then the potential is maximized when everyone acts invests the minimum possible effort. If A is exactly equal to n times B, then the potential is maximized at any point, does not matter. And if A is strictly larger than n times B, then you would like to invest as much as possible, so you invest 7. I remind you that in this example, 7 is the maximum possible investment. So that is the maximum of the potential. And please notice that this is are not all the equilibria, but these are exactly the points which people chose to do in the experiments which were conducted by Van Huyck at 1990. So actually, 1 year before Crawford formulated this generalization, Van Huyck conducted experiments which fit to a subset of those parameters, and exactly those points where the potential was maximized are exactly what the people did there. So it's still not clear actually how people act. It's in general, as I already said, it's an open question. But the potential, maximizing potential, definitely is an interesting refinement of the energy equilibrium. And at this point, we move to the other topic, which is called congestion game.